So in this video we're going to go over the trace of a matrix, and you denote, if a matrix name is A, you denote the trace of a matrix as TR, trace, the trace of A. So the trace of a matrix is very simply defined as, if you have a square matrix, it has to be a square matrix, then the trace of the matrix is just the sum of the diagonal elements on the matrix. So it has to be square, it has to have a main diagonal, you just add up the terms in the main diagonal. So for example, for this matrix A right here, the trace of A is simply the sum of the diagonal elements. So it's 1 plus -1 plus 7, which is just 7. That's the trace of A. And if I were asked to calculate the trace of B, what I would say is the trace of B does not exist, because B is not a square matrix. So a trace is only defined for square matrices. And then the trace of a matrix does have some properties that are associated with it. So the trace of the sum of two matrices can be found by taking the sum of the individual traces. The trace of the product AB is the same as the trace of B times A, and this is in spite of the fact that matrix multiplication isn't commutative. The trace of a scalar, this is little c, so little c is just some real number. So the trace of a scalar times matrix A can be calculated by taking the trace of A first and then multiplying the number that you get by the scalar c. And the trace of A is equal to the trace of A transpose. So let's say we were trying to prove property 1. Well, one thing I think is handy to do sometimes is just to think about what things look like. So for example, if you have matrix A and you know the trace of A is the sum of the diagonal elements, it could be useful to think about what the diagonal elements look like. You know, this is element A, row 1, column 1 is on the main diagonal. Row 2, column 2, the row and column number must match if you're on the main diagonal. The row and the column is the same. So A11, A22, all the way down. If this is an n by n square matrix, then this last element is going to be an A sub nn. It's going to be in that position. And matrix B is going to be kind of the same. We don't need to know what these other guys look like because the trace only cares about the main diagonal. So for B, it's going to be B11, B22, all the way down. There's going to be a guy here, BNN. It's going to be the last element on the diagonal. So when you take and add A plus B together, you know that when you do addition, you get the sum of corresponding elements. So the trace of A plus B is going to be the sum of the diagonal elements on A plus B, but A plus B's diagonal elements are just going to be the sums of the corresponding elements from A and B. So you're going to have A11 plus B11. The next element down on the diagonal is going to be A22 plus B22. All the way down, the guy in the bottom corner is going to be ANN plus B sub NN. That's what the main diagonal is going to look like. And we want to know what this looks like when we're trying to do a proof like this. Hey, the trace of the sum A plus B equals the trace of A plus the trace of B. So this gives us an idea of what we need to do. So for example, we start off, we'll let A and B be matrices, square matrices of the same size. That way we know we can add them. So we'll let A and B be square matrices because the trace is only defined for square matrices of the same size, because if they aren't the same size, we can't add them. And then what do we know? Then, well, we can calculate the trace of A plus B. Then the trace of the sum of the two matrices is equal to, it's just the sum of the elements on the diagonal. So it's going to look like this: A11 plus B11 plus the next element down is going to be A22 plus B22 plus blah blah blah. We don't know how many elements are going to be on the diagonal, but if these are n by n matrices, then we probably should even say that here. Let A and B be square matrices of the same size, we could say this even better. We could just let A and B be n by n matrices, and that takes care of that. And then that helps justify the use of n here in these positions. It's probably a better way to do it. Let A and B be n by n matrices. So the trace is going to be calculated by taking the sum of the elements on the diagonal, so all the way through A n n plus B n n. And then we want to remember that the little a's and little b's are just real numbers. They live on the real number line, and real number addition is both commutative and associative, which means we can regroup these real numbers so that the a's are grouped together, a11 plus the a22 plus blah 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 plus a sub nn plus, now we can group the b's, b11 plus b22 plus blah 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 plus b sub nn. And then we want to recognize is that this grouping right here, the sum of the a's, is just the trace of A. Plus, bringing the plus sign down, and this sum of the b's is just the trace of the matrix B. And so now we see that the trace of A plus B is equal to the trace of A plus the trace of B as desired. Thus, the trace of the sum is equal to the sum of the traces as desired. That's what we were trying to show, and that ends the proof of that particular property.